Hello. Today I'm going to be talking about dielectrophoretic multiphase flow separation. And before I get into what dielectrophoretic means, I'm going to tell you a little bit more about flow separation in general and why that's really important for space systems. Multiphase flow separation just means trying to separate some combination of liquids, gases, and or solids. And typically on Earth this is pretty simple. Bubbles will just float up out of liquids, or a rock, if you drop it, will just fall to the ground. But in neutral buoyancy environments, like on the International Space Station, this isn't so simple. You'll see in this video, an Alka-Seltzer tablet generates bubbles in this water droplet, and they just stay inside of the droplet. And this can be a big problem for fluid systems in space. For example, if you're trying to transfer propellants, if you're trying to split water to make oxygen, or just generally trying to manage fluids. Bubbles in fluid lines can cause severe pressure drops, blockages, and depending on the system, even complete failures. So we need a way of removing these effectively. So one common way of removing these bubbles is by using something called a capillary wedge. So if the flow is moving from left to right in this image, and let's say you have a big bubble that starts near this corner here, the bubble, if it's touching the walls, will be sort of pushed up as the liquid is wetting into this corner here. So what happens is the bubble will get pushed up, up more so, until it reaches a point here. And so this is kind of what that looks like in space. So this video here is from the capillary channel flow experiment pioneered by Dr. Louisville. And what it shows us is that the larger bubbles, as they interact with the walls, like we talked about, do get pushed out, but these smaller bubbles that remain will continue to be a problem. So that's what we're working on getting out. This is where dielectrophoresis comes in. By putting electrodes along the walls of the capillary wedge, we can impart a body force on the bubble to remove it from the flow. And this body force works in conjunction with the capillary force, as well as the buoyancy force, to remove these smaller bubbles. Let's examine the equation for dielectrophoretic force. Now in our case, we have electrodes along the walls of a triangular wedge, and we have liquid oxygen inside with gaseous oxygen above it, as well as a small gaseous oxygen bubble. These two substances have electric permittivities, which are a material constant which tells you the polarizability of that substance in the presence of an electric field. So in this case, a liquid will always have a higher electric permittivity than its vapor, and so it will be attracted to the inner corner of this wedge, and that means that the bubble will be ejected outwards. In the case of a solid, likewise, the material of the higher permittivity of the solid or the medium will be pulled inwards and the lower one pushed outwards. So in the case of a triangular wedge, the dep force equation simplifies to this. And what we see here is it's related to those permittivities as well as the voltage applied to the electrodes and the wedge angle, as well as the radius, which will be a function of the bubble's trajectory, which is dependent on the whole wedge geometry. What we want to know here is, for what geometries, at what voltages, does this dielectrophoretic wedge make sense? So to do this, we need to simulate this problem. The first step in doing so is to find out, what does the liquid-gas interface look like? And we've chosen liquid oxygen because it lends itself well to dielectrophoresis by it being non-conductive, and it's also very relevant for space missions. Now, we find this liquid-gas interface by using surface evolver, and the next step is to determine how fast is the flow actually going throughout this wedge and where. And the final step is to determine if a bubble starts inside of that flow, what's its trajectory look like as it moves through, and how much voltage does it take to push it up to the free surface and remove it from the flow. If we want to know whether this bubble makes it out of the flow to join the gaseous oxygen up here, or if it doesn't, we need to know what forces are acting on it as it moves through the wedge. So we apply a voltage to these electrodes, and we see that there's a dielectrophoretic force which acts radially outwards from the vertex of the wedge. And depending on if it's on the moon or Mars, or if it's in freefall or orbiting like we saw on the space station, there will be a buoyancy force or not. After a time step, the dielectrophoretic force gets smaller since the electric field is weaker further away from the vertex, and is pushed out further until it impacts the free surface and is removed from the flow. So now that we know how the bubble moves from the vertex up to the free surface within a wedge, we need to know how the bubble travels as it goes downstream through the wedge. And this will tell us whether the bubble is removed from the flow or whether it remains in the system to cause problems further downstream. So to do this, we determine the velocity profile along a given cross-section using a method outlined by Dr. ISRU. And with this information, we now have everything we need to know to track the trajectory of a bubble as it moves through a wedge. Since we want to find out when the dielectrophoretic wedge works well and when it doesn't, we need to run a large range of test cases. And this would be testing different wedge geometries at different flow rates. To do this, we start in MATLAB, which generates a large range of files, which are then run using a Windows batch command in Surface Evolver. Surface Evolver, communicating back and forth and iterating with Python, determines what the interfacial shape is going to look like for each of those test cases. We then bring that data into MATLAB to analyze the trajectory of a bubble at a given voltage. We put everything together, and this is what we get. We see here is a given test case, where we see in blue is what the interface looks like inside the wedge. That's where the gas and the liquid touch. And this red dashed line shows where the bubble goes from starting up to hitting the interface. And this is the minimum voltage required to do so, which is around 250 volts. Anything below that, we see 150 volts, and the bubble remains in the flow. Anything above that, we have here 500 volts, and the bubble is removed even faster. By running this analysis on a set of test cases, we can get a functional map of wedge angle and voltage pairs. So the wedges in this test case all have the same flow rate, but you'll notice that as the wedge angle decreases, the height of the wedge increases, such that all of the wedges in this test set have the same inlet area. If we look at the functional map, we'll see that as the wedge angle decreases, it takes a higher amount of voltage to expel a bubble of a given size. For smaller bubbles, it takes an even higher amount of voltage to do so. If instead we keep the average flow velocity entering the wedge constant between the test cases, and also keep the wedge height constant among the test cases, we see a different trend. That as we increase the wedge angle, it takes a larger amount of voltage to expel a bubble of a given size. All that being said, a key question remains. How does the simulated wedge perform at different levels of gravity? To answer this question, we want to examine a notional wedge of about 15 centimeters long and 2 centimeters high. We'll put it in microgravity, the moon, and on Mars at its critical flow rate, or the flow rate past which the flow will turn in on itself. We can use the axial position at ejection of a bubble, or in other words, how far along the bubble goes before getting ejected from the flow, as a measure of the effectiveness of the dielectrophoretic force at expelling the bubble. If we look at this graph here, in the solid lines we see for different bubble sizes, going from larger to smaller, the axial position of ejection at a given voltage. We'll see that as we increase the voltage, we get the bubble to expel at a much shorter length, which is significant because a shorter wedge length means higher critical flow rates, lower system mass, and overall better performance. If we look at the lunar and Martian cases, which would be the dashed and dotted lines respectively, we see a similar trend in that it takes a smaller distance, but it's still significant, but not as effective as in the microgravity case, due to the effect of buoyancy already aiding in the expulsion of the bubbles. To conclude, we analyzed the trade space for wedge geometry, flow rate, and voltage, and our preliminary results indicate that the dielectrophoretic wedge is an effective bubble expulsion device. However, we still need to analyze the relationship between the pressure drop, wedge angle, and critical flow rate, as well as the power draw of the system. That's all I have for today. Please feel free to reach out to my email if you have any questions at all, and thank you so much for watching.